Hello, everybody, and welcome back. We're still looking at our 2012 Euclid paper. This time we're up to question number 7. So we've got a light bulb and a written part. I think that's it. I don't think there are any more light bulbs. Nope, certainly not. And it is just two parts, so light bulb and just a written part. So A, in the diagram, triangle ABC has AB equal to AC, so we've got an isosceles triangle. And we know that angle BAC, that's this one here, is less than 60 degrees. Okay. Point D is on AC with BC equal to BD. So we've got another isosceles triangle in here. Point E is on AB so that BE the same as ED. So we've got a whole bunch of isosceles triangles. Interesting. If angle BAC, so the one they put up here, is theta, determine angle BED in terms of theta. So it's a light bulb question. We don't actually need to write anything down. So I'm going to draw a big triangle here. I'll write a little bit of my work on the side, but mostly this is going to be a verbal explanation. Okay. I'm also going to highlight for myself. This is one of the advantages of working in color. So bring colored pens or pencil crayons work great. But I'm going to highlight these in red so that I know, these two sides are the same. And then we also have D was chosen so that I get another isosceles triangle here. And then we had E, so this was an isosceles triangle. Okay, so the color really sort of helps me out there. So B, D, E, A, C. Okay, so other than the tons of isosceles triangles, we don't know any other angle other than theta. So that's probably why they're asking us for the answer just in terms of theta. Now, based on the picture, this looks to be bigger than theta. Maybe it's obtuse or something like that, but I'm not entirely sure. But we're going to have to sort of chase our diagram around and work out as many angles as we can. Now, if you've got an isosceles triangle, we know that the angles opposite the equal sides are themselves equal. Okay, so if we've got an apex angle of y, which we've got with theta here, we can work out what these two angles should be. So 2x plus y should be 180 degrees. So x should be 180 minus y all over 2. So this allows me to work out this angle and this angle in terms of theta. So 180 minus theta over 2, and you'll get the same thing over here. Now this one probably is going to need to be split up a little bit. Okay, but now we're down in this green triangle. It's isosceles, and I know one of the angles opposite the green side, so now I know this one over here as well. Okay. And yeah, I guess that means that ADC is congruent to BCA, which is kind of cool. But we can use these to work out that this should be theta here. And now I can work out this angle inside my smallest isosceles triangle. So the full angle at A is 180 minus theta over 2, but we already have theta of that accounted for, which we can write as 2 theta over 2. So we can write it as 180 minus 3 theta over 2. Okay, and that's opposite the blue angle, so we get the same angle over here. And we can either realize, these all need to add up to 180 and work it out, or we can note the similarity between this expression and this expression, and we can work on our apex angle. It's going to have to be 3 theta. Okay? And this, I believe, was the angle we were looking for. I probably should have highlighted that earlier when I was drawing my picture, but that is the angle we're looking for. So we just need to put 3 theta in the box. Okay? On the, if you want to, you can write a little bit more out, or just a clearly worded diagram, or clearly labeled diagram with these colors and a little bit of work on the side would probably be enough if you're worried. Okay? So 3 theta is our answer to 7a. And now what have we got with 7b? In the diagram, the Ferris wheel has a diameter of 18 meters and rotates at a constant rate, which is what you want for a Ferris wheel. When Calapo, I'm sure I'm not pronouncing that right, so if this is your name or you know how to pronounce this name, please leave a comment down below. I would like to learn how to properly pronounce your name. When Calapo rides the Ferris wheel, and it is at its lowest point, he is 1 meter above the ground. And they've started labeling these things for me, which is nice. When Calapo is at point P, that is 16 meters above the ground, which again, they've got in their little picture, it's rising. So that means we're going this way. And it takes him 4 seconds to reach T. Okay? So whatever this part of the circumference is, it takes 4 seconds to go that distance. And because the Ferris wheel is going at a constant rate, anytime we see that circumference being traveled, that distance being traveled, we'll know it takes 4 seconds. He continues to travel for another 8 seconds. It looks like that makes him go down to Q here. So it took 4 seconds here, 8 seconds here. Determine Calapo's height above the ground when he reaches Q. Okay, what can we do here? Well, we know the diameter is 18, so it's not that hard to work out the radius. I'm going to draw this picture here. That is not a bad circle, if I do say so myself. Okay, so they didn't give me the center of the Ferris wheel, but let's call it O. Got P here. T, I assume, for top, and then Q is somewhere over here. Q could be up here or down here, or could be right on the side. I don't actually know where it is. Oh, no. Oh, thank goodness for Control Z. That was a really good circle I drew. I'm gonna say Q is over here, but it doesn't really matter. And it's just a picture for me to sort of work with. Now we know the diameter is 18. I'm gonna say the radius is 9. Is really nice. Now we've got a bunch of points on this circle. It's a good idea to either connect them all up or at least connect them to the center. So we get some 9s here. Is Q going to be opposite P? Well, not on their picture. And although they say the diagrams are not drawn to scale, they're usually pretty good diagrams. But doesn't look like it, but okay, there's that possibility. Maybe P and Q are on opposite sides. And then it would be what? Then it would be 4 meters above the ground, I think. I don't know. We'll work that out later. Okay. Now I want. Let's drop some heights. So we know the ground is here. So I know this is 9. This is 1. Let's make A right below P. We'll make B right below Q. So what I want to work out is QB. As soon as I can figure that out, we're all set. Okay. So let PA be perpendicular to ground. Let QB be perpendicular to the ground. I'm surprised they didn't give the ground a name like CD or something. Which we could add in if we wanted to. GH for ground. Oh, great. Now I lost my ground. Making quite the use of that undo option here. Okay. Well, what can we do? We know that PA is 16. So we're starting to get some length there. One thing we could try to do is we could introduce maybe like C over here. I suppose while we're at it, we could do D here or E here, something like that. So make C so that OC is perpendicular to QC. So that's CB on TO so that QC is perpendicular to OC. And so we know that OD, we know that OD is 10. We'll say OD perpendicular to ground as well. We know that OD is 10, so if I could figure out something like OC, if that were 3, then suddenly I'd know this height is 7. So that's an approach. So we've used the diameter to get the radius, which is usually a good idea when you're working with circles. Okay. We've used this, well, we haven't actually used this 16. We've labeled the 16, but one thing we haven't touched on is the fact that it takes 4 seconds to go from P to T, and it takes 8 seconds to go from T to Q. So we should probably use that in some way. Now, what you could say is the Ferris wheel rotates at a constant rate. So it sweeps equal angles in equal time. And so if we give this angle a name like theta, we can see that, okay, halfway here is going to be another theta, and then this is going to be 2 theta. So what we can conclude is TOQ is twice theta, where theta is POT. Okay? Because it takes twice the time to get twice the angle. So we'll put a little 2 theta here. We also have got a 9 up here as well. Now, I had said we might want to relate. We haven't used the 16 yet. We've labeled the 16 yet. I did say we have the option of dropping a perpendicular like that. I think it might be wiser to use this one. That way we're using this theta here. We might get some trigonometry that we can work with. Okay, so that's what we're going to do. So I'll say, I'll use blue for this. Okay. We're up to E. Let E be on, I'm going to change this retroactively to TD. Okay. So let E be on TD, so PE is perpendicular to OE. Okay. Then what can we see? We know that OT is 9, which is fine. Just based on the last question, because the last question had a couple isosceles triangles, and sometimes they group things together. I'm noticing, let's highlight all our 9s here. We have potentially some isosceles triangles to work with as well if these right angle triangles don't work out. In fact, this one here, TCQ, I'll put in purple, might be very nice because it's a right angle triangle with this sneaky isosceles triangle in it. But we'll think of that in a moment. So we know, what can we say? Height PA is the same as ED because, well, PEDA is a rectangle. So PA is equal to ED, 16. Now I know that OD is 10. It's the 9 plus the 1, the Ferris wheel is above the ground. We can see that EO is 6, and so that gives us, in PEO, it's a right angle triangle with 9 here and 6 here, and theta here. So we could work things out like, well, we could work out the other side by Pythagoras, and then we could figure out the sine, cosine, tan, if we wanted to try and do this question with trigonometry. Okay? And we might very well do that. This is not a triangle I recognize, because this is, what, the 1, 3 halves, and I don't even know what the other side would be. It would be 9 quarters minus, so root 5 over 2. That's not a triangle I'm familiar with. I'm not familiar with the angles in there. So we'll see if we can find something else. Maybe these isosceles triangles will help us out. Let's redraw the picture. Not nearly as good as a circle as I had it the first time. better, I guess. But I want to redraw it. So we got Q down here, and I've got these are it's isosceles, and I know this is 2 theta. And as I remarked in part A, if you know the apex angle, this should be 180 minus 2 theta all over 2, which should be 90 minus theta. So both of these are 90 minus theta. Okay? But in that bigger purple one, if we have 90 minus theta here and a 90 degree here, this angle must be theta because it's got to add with the 90 minus theta to be 90. Okay? So we should probably write that up. So here's what you'd say that this was OTQ. So OTQ isosceles. So angle OTQ is 90 minus theta. So we've got this 2 theta here labeled on our picture. And then this was C, I think. Triangle TCQ is right angle triangle. So TQC is theta. And since it's a right angle triangle, then we can see that triangle TCQ is similar to triangle O has the 90, has the theta at it, so O and Q correspond. E was the 90 degree angle, so PEO. Okay. So we got C here, O here, 9 here, and this mystery length, which I'll call X. I did say a while ago if we could work out X, I said if it was like 3 or something, we'd work this out. QB, I can see, is going to be OD, or 10 minus X. So let's see if we can work that out. We also have another 90 degree triangle in here. And we know, so if I call this 6y, this has got to be 9y. So let QC be 6y. Then TQ is 9y. And we get a few relationships. So by the Pythagorean theorem, 9y squared is going to be 6y squared, so 36y squared, plus 9 plus x all squared. But then we have another relationship. 9 squared, 81, is 36y squared plus x squared. Okay? Let's take these two and subtract them from each other so that we get rid of that 36y squared that's in both of them. X squared, and we can expand it out, 81 plus 18x plus x squared. And now it looks like when we subtract, we'll get 81y squared minus 1, which maybe we could factor. These two cancel out. The x squareds cancel out, and we'll get 81 plus 18x. Now, this still leaves me with x's and y's. But if we rearrange this second statement, I suppose we can. We could have just gotten rid of y anyway. So we'll do that instead. So we know 81 is 36y squared plus x squared. So we'll say 81 minus x squared over 36 is y squared. Plug that in. We'll get 81. Where we used to have y squared, we'll get this. Where we used to have y squared, we put this. And then 9 plus x all squared. We'll deal with that in a moment. So the 36 cancels out. There's a factor of 9 in each of these that cancels out. So it looks like we get 9/4, 81 minus x squared, is 181 minus x squared, plus, we'll leave it as 9 plus x all squared for another moment. If I subtract 1 from 9/4, I get 5/4. Okay, this is probably something we can now work with. So we'll say, we'll multiply by 4 on both sides. 981, oh, some of those 81s are going to cancel out. 18x and x squared. So we'll have 405 minus 5x squared is 324 plus 72x plus 4x squared. We'll bring it all over to this side. So we'll have minus 81, 72x, and then 9x squared. Can we... Oh, we can divide by 9 on both sides. That would work out quite nicely. And x minus 1, x plus 9. So either x is 1 or x is minus 9. Well, minus 9 can't be a length, but more than that, based on sort of the direction of the picture, they're talking about t. So we would have sort of a degenerate triangle, because c and t would be the same length. So pretty easy to dismiss that one. That tells me x is 1. So we'll draw our picture one more time. Q here, I think it was B. O here, D here, C here. This is 1. The whole thing is 10. So QB is O is the same as O. It's the same as CD, which is OD minus OC, which is 10 minus 1. So it should be, so Pala, or what was it? Kalapo. Kalapo is 9 meters above the ground. And there we go. So we spotted an isosceles triangle. You could probably do this with trig. I think it'd be a little messy, but you probably could just do it with trig. But I'm glad I spotted the isosceles triangle in here with the 2 theta, having done part A. Very well crafted question, I would say. And yeah, I guess the rest was kind of boilerplate. I'm trying to find a side. We're trying to find this height. You know, very easy to drop perpendiculars and let rectangles do the work. And there we go. Now, if you tried to do this with trig, let me know how it went. Was it easier than what I did? Was it harder? Because those angles aren't going to be very nice. But I think I'm going to leave it and move on to question number 8. So I'll see you for more of our 2012 Euclid next time.